This is Math 2020 Lecture 40. Today we will cover section 11.9, which is about representing functions as power series. So the goal of this section is to show that certain kinds of functions can be represented as power series. Turns out that not all can. And only within a kind of certain radius of convergence. So let's start off with an example that we all know and I particularly love, which is f of x equals 1 over 1 minus x. We know that this is 1 plus x squared, and so on. In other words, it's the sum of x to the n as n goes from 0 to infinity, provided that the absolute value of x is less than 1. And the reason why we know this formula is true, that this function 1 over 1 minus x is a power series, is because of it's a geometric series on the right side, and we know what it adds up to. Provided that absolute value of x is less than 1, it converges. Now the question is, what can we do with other kinds of functions? Like suppose, for example, I give you something that looks slightly different. Let's take f of x equals 1 over 2 minus x, for example. Well, you can play this this following game. We could write this as 1 plus 1 minus x, grouping the 1 minus x term together, and then provided that the absolute value of 1 minus x, which is the same thing as saying the absolute value of x minus 1 is less than 1, this is going to be the same thing as 1 plus 1 minus x plus 1 minus x quantities squared, and so on. Now it's more convenient to rewrite this as 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed plus x minus 1 to the fourth, etc., which can be then thought of as the sum as n goes from 0 to infinity of minus 1 to the nth power x minus 1 to the n, and that's a power series centered at x equals 1. So this is centered at x equals 1, and the radius of convergence is r, which is also 1, and it converges on the interval from x equals 2 to between 1 and 2. So that's the interval of convergence. So we've just now expressed this function f of x equals 1 over 2 minus x as a power series. So in some sense, we built a new power series from the old one, 1 over 1 minus x, by doing this very simple manipulation. Let's do another example. So let's consider the case of f of x equals x squared over 1 plus x. Now, we know that 1 over 1 plus x is a sum of a geometric series 1 minus x plus x squared minus x cubed plus x to the fourth, etc., for absolute value of x less than 1. Okay, which is the same thing as the sum, if you like, of minus 1 to the n, x to the n, and going from 0 to infinity. So therefore, if we multiply both sides by x squared, so you get x squared over 1 plus x should be the same as x squared times this sum. But that's the same thing as the sum minus 1 to the n, x to the n plus 2, as n goes from 0 to infinity. And this is absolute value of x is less than 1. So that's a simple example. And not much more to that. Okay, so let me now get to another result, or actual result in this section. It's the only result in this section, which is the following theorem about differentiation and integration of power series. So what's this about? So suppose you have f of x is a power series, as a function expressed as a power series, say n goes from 0 to infinity, with radius of convergence r strictly bigger than 0. So then we can think of this as C0 plus C1 times x minus a plus C2 times x minus a squared, etc. Okay, so then we can actually compute the derivative of this function term by term, and this is given by C1 times so C0 is a constant, has no derivative, C1 times the derivative of x minus a, which is 1, plus 2C2 x minus a, plus 3C3 x minus a squared, and so on. In other words, this is the sum, n goes from 1 to infinity, of Cn x minus a to the n times n. This is actually also has radius of convergence r, the same radius of convergence that's up here. And similarly, we can talk about the integral of f of x dx. And that's given by integrating term by term and adding a constant. So we'll put the constant at the beginning, c plus summation. I'll just write out the series form. N goes from 0 to infinity of Cn x minus a to the n plus first power over n plus 1. So these are the two results that we have here. There's this one and this one here. And here the radius of convergence is always r in both cases, where r is the original radius of convergence of the original series. Okay, so let's see how this can be used to our advantage. So let's consider the following thing. Let's consider f of x equals 1 over 1 plus x squared. So this is a geometric sum of a geometric series, 1 minus x squared plus x to the 4th minus x to the 6th, and so on, which is sum minus 1 to the n, x to the 2nth power, n going from 0 to infinity. Okay, let's integrate f of x. So the integral of dx over 1 plus x squared, according to this the theorem that I proved, should be the sum n goes from 0 to infinity of minus 1 to the n over 2n plus 1 x to the 2n plus 1. I've integrated term by term, and so it's so that's the answer. But then we have to add that plus c. So now we know that the left side, a particular antiderivative of the left side, is arctangent of x. That's from chapter 7 in the book, Methods of Integration. The derivative, the integral of 1 over 1 plus x squared is arctangent x. And so this is going to be the sum, n goes from 0 to infinity minus 1 to the n over 2n plus 1, x to the 2n plus 1, plus c. But now what is c? We have to compute it. The way you compute it is plug in a value of x, your favorite value of x. So if we set x equal to 0, arctangent of 0 is 0. And the right side, if you plug in 0, you get 0 plus c. So that says that c equals 0. So therefore, we get the following expression: arctangent of x is equal to the sum, which I'll write out. It's So when n equals 0, you're going to get x, and then we're going to get minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. And here, we need to know the absolute value of x is less than 1, because way back when, we knew the radius of convergence of this series was 1. So the absolute value of x is less than 1. So now we have shown this very interesting expression for the arctangent function. Okay. Here's another example, which I think is kind of cool. So let's look at, again, our geometric series, 1 over 1 plus x, which is summation minus 1 to the n, x to the n, and absolute value of x should be less than 1 because it has a radius convergence of 1. And this n is going from 0 to infinity. Let's integrate both sides to get the integral of dx over 1 plus x is a constant plus sum n goes from 0 to infinity of minus 1 to the n plus 1, x to the n plus 1 over n plus 1. So now we know the antiderivative of the left side by doing a substitution is ln. Let's ignore the absolute value here for a moment, 1 plus x. And that's going to be given by c plus this sum. Let me write out the terms of the sum. When n equals 0, you're going to get minus, this is not a minus 1 to the n plus 1. This is a minus 1 to the n. Okay, so it's going to be n equals 0. You're going to get x over 1 minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. It's alternating. So now we can compute the constant by setting c equal to 0, x equal to 0, sorry. To get ln of 1 is equal to c, because the remaining terms vanish, but ln of 1 is 0, so c is 0 in this case, again, in this example now. So therefore, we get the following expression. I'll write it in blue. ln of 1 plus x is given by x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. This should not be a 5 over here, it should be a 4. And so on. Dot, dot, dot. So that's sum minus 1 to the n, x to the n over n. N goes from, I actually have to put an n minus 1 here. N goes from 1 to 0 to, nope, it's actually an n. N goes from 1 to infinity. If n equals 1, yeah, this works out. This is the correct formulation. Okay, so that's the expression. We get an expression for the ln function in this way. And here again, the absolute value of x needs to be less than 1. That's the radius, it's coming from the radius of convergence. Okay, so that's an example. Let's do another example. Let's consider f of x 1 over 1 minus x again. So we get 1 plus x squared and so on. And let's consider differentiating both sides. Now the derivative of the left side, so this, remember, the right side, first of all, summation x to the n goes from 0 to infinity. So now let's differentiate both sides. The derivative of the left side, if you think of it as 1 minus x to the minus first power and use the power rule, we get 1 over 1 minus x quantity squared. And the right side we can differentiate. We get the sum n goes from 1 to infinity of n x to the n minus 1. So in other words, 1 over 1 minus x squared is equal to 1 times x to the 0, which is 1, plus 2x plus 3x squared plus 4x cubed and so on. And here the absolute value of x, of course, is still 1. Okay, that's kind of neat. So let's consider now a related example. Let's take what we just did and differentiate it again. So we have 1 over 1 minus x squared we saw in the previous example is summation n x to the n minus 1, and going from 1 to infinity. Let's differentiate again. So if we differentiate the left side, so we can think of this as 1 minus x to the minus 2. If we differentiate it, we get minus 2 over 1 minus x cubed times the derivative of the inside. So you're going to get 2 over 1 minus x cubed as the left side. And the right side is going to be the sum, n goes from 2 to infinity, of n minus 1 times n times x to the n minus 2. And I want to, for making it nice, let's divide both sides by 2. So you get 1 over 1 minus x cubed is equal to a half. Sum n goes from 2 to infinity, n minus 1 times n, x to the n minus 2. So you can think of this as 1/2 times 1 times 2 times x to the 0th power plus 2 times 3 times x, plus 3 times 4 times x squared, and so on. And we can bring the 1/2 in. So it's 1 times 2 over 2 times plus 2 times 3 over 2 times x plus 3 times 4 over 2x squared, and so on. Or if you want to write it in series in sigma notation, this is n minus 1 times n over 2 x to the n minus 2, and going from 2 to infinity. And it's even prettier to write it in terms of a binomial coefficient, because n minus 1 times n over 2, if you know binomial coefficients, this would be the binomial coefficient n choose 2, n to the n minus 2. So we got this kind of cool expression for the function 1 over x cubed, 1 over 1 minus x quantity cubed, as n choose 2 x to the power of n minus 2. If you don't know what a binomial coefficient is, don't worry about it. Well, that just about covers section 11.9. This was not a hard section. And most of the examples in the exercises section of this part of the text are just playing the same kind of games. Okay, so that's it for today.